First of all, I'm terribly sorry for this small delay because I was so stupid that decided that I'm speaking 2:30, and thanks Igor to find me to bring me here. And also I want to thank Henrique and all colleagues from Rio for this nice opportunity. I'm the first time here, and I'm completely I like the place, and I'm happy that I have this opportunity to speak here. And today I will speak about something which, in fact, I did long time ago, almost started to study and to write something about this almost 20 years. First paper we published with Sasha Odesky. It was in 2002, but it was written earlier. And my talk will be basically upon these results with Sasha Odesky, who is now in Brock University in Canada, and my former PhD student, Serge Tanier-Pilap, who is unfortunately for mathematics, and fortunately for him, now works for Credit Suisse at Zurich, and Giovanni Artenzi, who is from the University of Milan, who was my postdoc at that time. And so we wrote a couple of papers with them, and very recently, due to Misha, I revised some things which we didn't finish with Sasha and with Giovanni and Serge, and just prepared a talk for his seminar in Moscow. Then Bursztyn asked me to do the same in another conference. So I started to write small new papers. So I will tell you some comments. Basically, my talk will be geometric comments to so-called Blue Kiev preprint of Sasha Odesky and Boris Feigin, my Russian colleagues. They wrote this preprint. It was the first preprint in elliptic Sklenin algebras. And it was never published, in spite of many people involved in this activity, and in spite of many papers wrote by Sasha, Borya, and Vandenberg, Artin, Tate, Paul Smith, many good mathematicians. This preprint was never geometrically interpreted. It was interpreted. It was a kind of just statements, algebraic statements, mainly without demonstration, and it was not clear. And when I asked the author said, said Sasha, geometry you should ask Borya. And Borya says, oh, I forgot everything, you should ask Sasha. Sasha, he's young, he has to know. So it was a kind that I feel that I need to make some comments to this. And some comments became maybe future paper, and some of these comments are very interesting from the viewpoint of geometry. So I will start with a reminder about Poisson structures, basically about holomorphic part of the story, and then important subject of my talk is the invariance with respect to Heisenberg group. This invariance with respect to Heisenberg group, it's very powerful, not only for Sklenin, Odesky, Feigin algebras, but also just, for example, from the viewpoint of study in this audience, people like probably to study modularity and unimodular Poisson structures. So, for example, Heisenberg invariance, if you speak about quadratic structures, implies immediately unimodularity. It means that this is a good hint to try to speak about quantization in the framework of Calabi-Yau. And recently was good result of Brent Pym and Travis Shedler. They proved that odd Odesky-Feigin algebras, odd it means with odd number of generators, they are really Calabi-Yau. Well, then I will go to geometry, and I will describe symplectic foliations of two Odesky-Feigin elliptic algebras, and this is a main comment to this preprint. And interpretation of some Adesky-Fagan maps as a quantum analog of Cremona transformation in P4, in CP4. It will be also subject of my talk if I have time. And of course, I will start very, very carefully study the case of the next number of variables, in number 7, because odd Adesky-Fagan algebras, they are has some specific, I will try to explain you. So of course it's impossible to start to speak about Poisson structure without reminder what is a Poisson structure is. So it is a just infinite dimensional structure of Lie algebra on the functions, or some manifold, whatever at the moment, with the skew symmetry property and Jacobi identity, and of course this bilinear operation, as you know, it's B derivation, so it satisfies Leibniz identity for both arguments. And from geometric viewpoint or from algebraic, this structure can be described in terms of bivector, antisymmetric bivector field P, which define the corresponding operation by this coupling with two form given by wedge product of functions differential df and dg, and the condition of Jacobi implies by so-called Poisson master equation. This is a Scout and Nines bracket about which we heard so many good things yesterday in the framework of Jacobi manifold. And this, in other words, this Scout and Nines structure is nothing but Lie superalgebra structure on the polyvector fields on the base manifold. Well, also I will use the note. I will not remind you all details about Poisson structures. You know, might be better than me, might be better than me about them. I will not speak about analog of Darboux theorem by Weinstein. I just will remind you the notion of Casimir, because Casimirs play a very important role today for these comments. The Casimirs of Poisson structures, just a function which commutes with all other functions in the algebra. And also, I want to remind you the notion of symplectic foliation, because normally Poisson structure gives you by skew-symmetric matrix of this tensor, and this skew-symmetric matrix is not, generally speaking, non-degenerate. So there are some symplectic leaves where this matrix is invertible, where this matrix is really non-degenerate, and you can always take in the vicinity of some points the coordinates, such the foliations of this Poisson structure is given by a set of level equations for some constants. So in general, this dimension of leaves, generally speaking, is different. From leaves to leaves, you have a stratified set, you have a stratification, and only this dimension has only constant value on the open dense. But I will speak about very specific Poisson structures. I will speak about holomorphic Poisson structures. I will speak about complex manifolds, such that this bivector field P is given by sections of holomorphic skew two vector fields with a condition of 0 for Schouten brackets as an element in the sections of lambda 3. And the brackets locally, they are, if you take locally holomorphic functions, then the brackets also gives in the usual formula. This notion, very interesting, specified for low-dimensional complex manifold. For example, if your complex manifold is two-dimensional, then this tensor field is a section of K star, and you have anticanonical divisor, and you can easily see that this degeneration divisor has degree 3, and it means that you can imagine it like an elliptic curve or degenerate elliptic curve or combination of just three lines. And this gives you the example of so-called, for people who like case 3, and I know that there are some of them, non-commutative case 3 surface. If you have as a two-dimensional manifold P2, then K star is a polynomial degree 3, and vanishing of this bivector field, you have a vanishing on order 3 on the line at infinity. So you can think about P2 minus elliptic curve, or minus degenerate elliptic curve, or minus triple of line, like a kind of non-compact Calabi-Yau of dimension 2. In the case of threefold, there is also some specific, because in this case, lambda 2 is isomorphic to T star tensor K star, and you can attach to P one form theta, and this one form theta gives you the integrability condition, which is equivalent to the Poisson property. So this one form theta with values in K star satisfies this equation. So we have some, in threefold case, we have singular holomorphic foliations when this P is degenerate, and symplectic leaves of these foliations is given explicitly by the zeros of this one form. So if we have the case when some loci, when the tensor P equal to 0, then we have this loci as an intersection of two-dimensional Poisson submanifolds, Poisson surfaces. We can see this on the example of three-dimensional projective space. In three-dimensional projective space, K star is a polynomial degree 4. You have two sections, quadratic sections, or S1, S2. So you have two quadrics in P3. These two surfaces intersect by elliptic curve. And this is a geometric interpretation of the simplest algebra, Poisson algebra, which I want to discuss today. This is a picture of so-called Sklenin algebra with 4 generators. It was initial example what Sklenin studied. Of course, Sklenin had known this geometric image. He had used description of some integrable model. It was Landau-Ginzburg ferromagnetic. And Landau-Ginzburg ferromagnetic for philosophy of Leningrad school, of Fadeev school, it was some integrable systems. And the integrability of these systems, they proved using their R matrix, classical R matrix, and then quantization quantum R matrix. And this R matrix can be explicitly constructed like from the physical model, like a matrix which depends on some elliptic curve parameter. So Sklenin had very, very clever hint that this is a generally interesting structure, not only for this Heisenberg or Landau ferromagnetic, but for many other interesting purely algebraic constructions. It is interesting to study quadratic algebras with dependent on elliptic curve parameter. So to give the general definition, I remind you some specific construction of Poisson structures polynomial type. So general construction, Jacobi-Nambu, you know very well. Probably you have for set of n-2 polynomials in n-dimensional complex space, the operation between two functions on Cn, so I just suppose for simplicity that all functions are polynomials, and you can define the bracket by this formula, you take the volume given by the n coordinates, x1, xn, and then you take n minus 2 given polynomials, and you compute the function which is skew-symmetric bracket, gives you a skew-symmetric bracket between f and j. And of course, this function given polynomials q1, qn minus 2, they are Casimirs of this bracket. This bracket was introduced by Japanese physicist Nambu for n equal to 3, and this it was a first example of some kind of non-commutative quantization or non-Poisson quantization. He constructed an analog of quantum mechanics with this Nambu bracket, and in details it was studied by Takhtajan. Hauss-Sklenin algebra comes from Nambu Poisson structure. So let's consider this Q1, Q2, these two sections given two quadrics. I consider the affine situation, and I will briefly describe the relation between affine and projective Poisson structures. So Sklenin considers two quadrics in C4. One quadric is just x1, x2, x3 in squares, and second quadric depends on three parameters, j1, j2, j3, satisfying this condition. And in fact, using this second quadric, you can show that the parameters j1, j2, j3 from the physical model for which Sklenin constructed this quadratic algebra, these parameters are functions of Jacobi type, Jacobi sn, kn. They are ratios of them. And to have non-degenerate structure, you should have this condition. So the Poisson brackets given by two quadrics can be constructed by this Jacobi-Nambu principle. You have bracket between two coordinate function xi, xj, taking Jacobian of these two quadrics with respect to complementary two coordinates. So if you have, for example, 1, 2, here you have Jacobian with partial derivatives over x3, x4. And then you obtain this elliptic curve in the intersection. It is just a projective embedding of two quadrics in P3 given by four theta functions of Jacobi. So these coordinates, they came from this geometric description of embedding, projective embedding of elliptic curve in P3. So the question, of course, if it is just the case of Sklenin, or you can generalize it. It is interesting that the case for Sklenin algebras with three generators, Sklenin himself didn't consider. And it was independently, exactly in the same time, considered by Artin and his student Schelter, and then later by Tate, Vandenberg, and other people in the following context. So we can do the same. We can take for n equal to 3 the system ample line bundle, which gives you embedding of elliptic curve given by Hesse cubic in P2, and the coordinates x1, x2, x3 you can easily recognize theta 0, theta 1, theta 2 Jacobi theta function. Then you can apply to this equation the principle of Nambu-Jacobi structure, and you can obtain the quadratic brackets, homogeneous quadratic brackets in C3 between x1, x2, x2, x3. They are cyclically, and this is the derivative of this Casimir polynomial. So it is a trivial observation, but a highly non-trivial statement of Schelter and Artin that you can, in some sense, consider non-commutative associative algebra, which has this algebra, Poisson algebra, as a quasi-classical limit, and this algebra is a graded algebra which satisfies the so-called PBW, Poincaré-Bergov-Witt conditions. And the conditions that Poincaré-Bergov-Witt for this graded quadratic homogeneous algebra is explicitly equivalent that coefficients of brackets, non-commutative brackets, satisfy to equation of elliptic curve in Hesse form. I have no time to be more precise here, but I want to say now that you can do the same for any cubical equation. So, for example, you can consider these fibrations of surfaces, and you can consider configurations of various degenerated elliptic curve. With each configuration, you can define an analog of three-dimensional Sklyanin algebra. It is interesting that they are really generalized Sklyanin algebras, and recently people studied their PBW property. Some of these algebras satisfy PBW, some of these pictures satisfy to generalize PBW. This was in 2014. Natalia Yudu and his collaborator in the preprint of IHS, I don't know where it is published, they wrote very nice description of all non-commutative algebras corresponding to these configurations. Now the question about the relations of holomorphic Poisson structures in affine and projective space. This relation is well known. I will just quote our result with Sasha Adesky of 2000. And of course, it is a partial result, general result, general conditions, general relations between these two structures in affine and projective spaces. They were described by Sasha Polishchuk in his paper about algebraic geometry of Poisson brackets. And very recently, they generalized it with his Chinese co-author in the very recent paper, very beautiful, interesting paper, where they established the relation between Sklyanin algebras and derived algebraic geometry. But for us, it was enough just to compare the brackets in homogeneous coordinates on Pn, on Cpn, and affine part of this in non-homogeneous. So the extension, compatibility of these two structures impose condition that the maximal degree is, it means the length of monomials in non-homogeneous coordinates is only 3. It means if you have brackets of this type, this factors y, they have degree exactly equal to 1. That's why it is interesting to study the quadratic Poisson structures. In the case of Sklyanin algebra, we will have exactly this quadratic algebra. Now, formal definition, because I spoke many times about Sklyanin, Adesky-Feygin algebras, and I didn't say the definition. So I will speak about associative quadratic algebra, big Q, which depends on two parameters, n, k. I will suppose sometimes that these two parameters are mutually primes. Y, big Y, it's a smooth elliptic curve, smooth, normal elliptic curve, which normal means that this elliptic curve admits embedding in projective space by some ample linear systems of sections like theta function in the case of P2 or P4. And also, I suppose that this algebra depends on some complex parameter. In fact, this complex parameter I will suppose to be a point on this elliptic curve y. And it is a kind of deformational parameter in the sense that if this number, if this eta equal to 0, then my algebra is nothing but a polynomial ring with n generators. So it is a kind of deformation of a polynomial ring, but very, very special deformation, because I suppose eta to be a point on the elliptic curve. And the description of this algebra is the following. So I will consider the elliptic curve like a quotient by lattice gamma. And this lattice gamma has a period, real period 1 and complex tau with, as usual, imaginary positive part, then this algebra can be described as an algebra with n generators and n times n minus 1 over 2 relations. And these relations, quadratic relations, these relations has the coefficients in terms of theta functions of degree n on this given elliptic curve in 0, in minus n, and minus eta. This is a constant coefficient. I will not explain why these relations appeared in such form. It was, first of all, hint by Adesky and Fagin, but it was also follows from the description of geometry of projective geometry of elliptic curve in the book of Hulik. Funny that neither Adesky nor Fagin, they didn't know this book, but they had this beautiful observation. So from the viewpoint of graded structure, this is just usual graded algebra with constants. Degree 1 part which has dimension n, and you can imagine that this is a kind of space of theta, n theta function degree n. And then you have a symmetric degrees of this first degree 1 component. The multiplication, star multiplication in this algebra compatible with this gradient, so the products of elements of degree alpha and beta belongs to the Q with degree alpha plus beta. So we have the usual Z gradient. With a good PBW property, it means that the Hilbert function of this algebra has this standard form. For example, for n equal to 3, it is 1 over 1 minus t in degree 3, which was discovered by Shelter in his thesis. And this algebra satisfied some interesting duality property. If you have k and k prime compatible with 1 by the residue n, then these algebras are isomorphic. Normally speaking, if you don't have this, these algebras are not isomorphic. Moreover, if you take different eta, you have in principle different algebras. But they admit very nice symmetries. For example, if you have the shift of index of argument, indices I and goes to indices I plus 1, and multiplication by generators with the roots of unity, then you have the automorphisms of the algebra Q and K. So it means that this algebra admits, like we will see, a Heisenberg group action. And Heisenberg group action impose very, very interesting consequences for geometry and for Poisson geometry related to this algebra. So it's a flat deformation of our polynomial ring, which corresponds to eta equal to 0. And this is a very special deformation because being a point on the elliptic curve, of course, it is not any deformation because when you shift by eta, it means that you use the abelian structure of the initial elliptic curve. So you should be very, very careful writing, for example, explicit multiplication for this in this algebra. Maybe I will write you this multiplication just to show that no white chalk. Okay, doesn't matter. So let's suppose that we have F1, F2 in Q1. Then F1 star F2, it's a function of U and V such that then you have what do you have? You have f u plus 1 plus eta f2 u minus eta times, so you have the product and you have the deformational coefficient theta u plus n times, just a moment, I will check. I forgot. U minus v, sorry, u minus v plus eta divided by theta of u1 u minus v plus f1 v plus eta f2 v minus eta times theta v minus u plus n eta divided by theta v minus u. So this is a multiplication which deforms this multiplication. In general formula, it is just a formula deformation of product in symmetric algebra, but it is absolutely the same structure, and it is easily clear from this that this is a non-singular multiplication because of the cancellation of poles due to theta function relations. Nice result which we proved with Sasha Odesky in 2004. It's for people who are seeking some integrability in this, that if you have Sklenin algebra with even number of generators, so it's n equal to 2 times m and k equal to 1, then in this algebra there is m exactly half of the number of variables, m commuting elements, and all these elements are degree. All these elements have degree m. It is non-trivial, but maybe not very difficult, but non-trivial result. And this non-trivial observation has some interesting consequences. For example, for what Igor told today about separation of variables. If you consider the algebraic scheme behind of separation of variables, you can use this result and the technique which we have used to prove integrability of some separated integrable systems in separated variables. For example, very difficult integrability of RSOS vertex models, for example, Varchenko and Felder aperiodic model, is completely almost straightforward using our theorem, which we have wrote as an application of this result. Well, now about Poisson, because we are in Poisson world. Of course, if we have this algebra, we should have some kind of quasi-classical limit. And I will denote this quasi-classical limit for degree 1 deformation in eta by q and k of y. And this algebra, it is also non-trivial result. If we have common divisor, maximum common divisor between k plus 1 and n L, then we have L Casimirs. This Casimirs form a centrum of this algebra, and we can consider the degrees of generators of these elements. And it is interesting that now I will forget about n and k, and I will speak about n equal to 5. Why? First of all, because you know elliptic curves embed in projective space for n equal to 3, for n equal to 4 by this theta function. So they are in the origin of, they have complete intersection of subvariety. If you have n equal to 5, embedding of normal quintic elliptic curve in P4, it is a different story. I will speak about this story a little bit. So first of all, it is the first interesting case because there are two different Poisson tensors for n equal to 5. If I told you that there is a isomorphism nk of y and nk prime of y, if k prime compatible with 1 modulo n. But if you take, for example, I didn't tell you, for example, that it is not interesting to study qn n minus 1 y. This algebra is always abelian. It is proven by Adesky and Fagin in his first paper. That this is not interesting. It is always abelian. So if you take n equal to 3, so you can consider Q31 and Q32, and Q32 is abelian. Nothing interesting. If you have n equal to 4, you have Q41. It's a Sklenin algebra which corresponds to this quantization of these two quadrics. But you have also Q42 and Q43. Q43 is abelian, and this, from this condition, it gives you the same algebra. So n equal to 5, it is the first case when you have really two different Sklenin algebras. And the geometry is much richer. And that's what the object of my talk, to describe geometry of Q51 of y and Q52 of y. So this also, from the viewpoint of Hamiltonian structure, it is quite obscure because Sasha Adesky in his small note just shows that if you take Qn1 for n arbitrary Qn1, it is always 3 Hamiltonian. It means that there is 3 Hamiltonian structures. Naively speaking, you cannot understand why it is 3 Hamiltonian because, for example, you can consider the projective model of your elliptic curve in Weierstrass form. And in Weierstrass form, there are two modular parameters, G2 and G3. And this G2 and G3 you can consider like the coefficients in the Casimir of degree 3. And taking the principle of these brackets, you can find that there is a three family of quadratic Poisson structures given by this elliptic curve. So I told you very, very roughly, but it is more or less this the reason why it is 3 Hamiltonian. Unfortunately, it is not clear. For example, if you have Q and K with K different from 1, and for all odd-dimensional algebras, what the kind of integrable systems are. If you have these 3 Hamiltonian structures, but we don't know what kind of 3 Hamiltonian integrable systems behind this 3 Hamiltonian structure. We don't know it. And also, we had a chance to check if there is some compatibility condition between these two algebras, considering these two structures like structures on P4. No, they are not compatible. These two algebras never compatible. This is also bad news for integrable systems. But good news is that there is a good algebraic description of these algebras. They admit a description in terms of Pfaffian sum skew-symmetric matrices. And these skew-symmetric matrices, not directly, but as I discovered implicitly, related to Poisson tensors of Q51, Q52. So this Poisson description, it's a kind of new observation. The algebras, the brackets between algebras, they look a little bit ugly. I want to say that this is exactly the case when the ugly formulas so ugly that they are beautiful. Yes, because it looks ugly from the very beginning, but you will see that in fact they are beautiful. So this is algebra Q51. It's quadratic algebra given by these formulas. The parameter k, it's a parameter related to the tau, to this modulus of elliptic curve. And the centrum of this algebra, it is also just an ugly formula, but you will see that it is in fact beautiful, is given by this quintic polynomial in 5 generators of this form, which is also dependent on this parameter q. So this is a typical quintic, and level of this quintic, people in algebraic geometry should recognize immediately it is one of these Calabi-Yau threefolds given by hypersurfaces of the level in P4. And you will see how it goes from the Poisson geometry. The second elliptic structure looks like this, similar but slightly different. And of course, the first natural question, how this, of course, there is a corresponding quintic also for Q52, also different from this one. And you will see the difference, the reason of this difference. And it is interesting to discuss if there is a change of variables which transform one structure to another. In some sense, the answer is yes, in some sense. But it is a birational transformation, which is nothing but Cremona quadricubic transformation in P4, classical quadricubic Cremona related to elliptic curve. So just a brief reminder what the Schrödinger representation for Heisenberg group. So we have an n-dimensional vector space with basis Vi, and then this Schrödinger representation of Heisenberg group is given by these two operations, this operation of shift of indices, like I told you before, and multiplication by root of unity, epsilon I. And then this Heisenberg group is a central extension by the group of ends of unity, the just Cartesian product of Z mod n. As I told you, Heisenberg group gives automorphisms of Sklenin algebra, and these automorphisms, they are compatible with gradient, and also they are compatible with quasi-classical limits. So they act on the corresponding elliptic quadratic Poisson structures. I speak about elliptic quadratic Poisson structures on Pn-1. In this case, this correspondence between homogeneous coordinates and non-homogeneous coordinates is easily achieved. It is, for example, in details studied how these structures one-to-one correspond in the quadratic case by Brent Pym in his thesis. And also probably it follows from initial Polishuk description. But Brent did it very, very clearly. So this structure we will now identify due to Adesky and Feigin and to Polishuk in two different ways. They described it from different positions, but obtained the same result. We can interpret these algebras like Poisson algebras on some moduli space of vector bundles. For the case of Adesky and Feigin descriptions, they considered degree n and rank k+1 vector bundles with fixed parabolic structure. So they have a flag in this vector space ck+1 on the elliptic curve, and then they have the following result. Let's consider this moduli space of k plus 1 rank bundles on the elliptic curve with a given one-dimensional subbundle. Then, using ATIA notation of undecomposable bundle of degree n and rank k, C and k, we can consider the moduli space of exact triples and these extensions up to isomorphism. And the set of this moduli space is exactly Pn minus 1 projective space with a projectivization of this x1. And this space is a Poisson manifold, holomorphic Poisson manifold. And the Poisson structure on this manifold is a classical limit of big Q and K as a homogeneous quadratic structure on Cn. So this theorem of Adesky and Feigin, they used, I have no time to give you the description, but the idea is they used R-matrix arguments. They used, if you want more precisely, they have used the arguments of Manin pairs to establish this Poisson. Similar, in more detail, similar computations were done in the thesis of Viti Ginzburg student Baralia. And Sasha Polishuk proposed another description of these algebras. He considered moduli space of triples. Triple, it's two vector bundles over elliptic curve of fixed degrees and fixed rank with a given slopes, with a given stability conditions, and the homomorphism of these vector bundles. If you take special choice E2 or Y and fix E1 like a vector bundle E, then the moduli space of this triple coincide with Adesky and Feigin moduli space. So he considered a little bit more general description, but in the interesting case for elliptic curve, he proved the following result, that there is a birational transformation which compatible with Poisson structures in sense of Adesky-Feigin, and this birational transformation transform moduli space of vector bundles of degree n and rank k with moduli space of vector bundle of degree n and rank phi of k, which phi of k is an integer number which solves this compatibility mod n condition. For example, if you take n equal to 5, which is interesting for us, first of all, you can identify it as a result of Polishuk. You can identify this moduli space with projectivization of sections of some stable vector bundle of degree n and rank k plus 1. And for n equal to 5, we have the following solution of this compatibility condition. You have R prime equal 1 minus 1 over 2 modulo 5, which gives you 2. And so you have a birational transformation from Q51 to Q52, and vice versa. So now I want to precise what is a birational transformation, because Polishuk didn't do it, and he was very surprised when I showed him this. This birational transformation you can imagine like a transformation of quantum Adesky and Feigin algebras. And this was the only thing which Adesky and Feigin wrote in this Kiev preprint explicitly. They said that if you take quantum Q51 and Q52, just as example, then you can consider the Q52 as a subalgebra in Q51 generated by 5 elements and 10 quadratic relations. But in opposite way, you can consider Q51 also as a subalgebra in Q52, also with 5 elements and 10 quadratic relations. Now, of course, if you have this embedding, you can consider the composition. Embed Q51 to Q52 and then back to Q51. And it happens that the initial generators x1 multiply by some polynomial of degree 5. This is a centrum, which I showed you. And also, they didn't compute it, they just proved that it exists. And then they considered the similar transformation in opposite way. I was very, very surprised, and I wanted to precise what these polynomials are. And then the geometry of this is the following. Odesky didn't do it, but Fagin, in his talk in École Polytechnique in '94, when Henrique invited him for a few weeks to École Polytechnique, and we have a lot of discussions. He told us a lot. For example, he told us how these symplectic leaves for Q51, more precisely for Qn1, are constructed. So for n equal to 5, we have dimension 0, dimension 2, and dimension 4 symplectic leaves. Two-dimensional, dimension 0 non-interesting, dimensional 2 symplectic leaf, it is just a cone of the elliptic curve. You can identify elliptic curve with the first secant variety of chords, degree 1 of y. But if you take the second secant variety, then you can consider cone over all unifications of this chord, and then it is not elliptic curve, it is a new variety, it is a surfaces. It's a surface, and this surface is exactly the interesting object in this geometry, because the degenerate loci of this secant variety is exactly this secant variety degree 1. It means that the very elliptic curve. And this is a typical property only Q51, because the degeneration loci of this in other algebra is quite different. And this was the point which provide the demonstration of Bondel conjecture by Brent Pym and Marco Gualtieri. They've used this property of Q51, that the generation loci of secant variety of this four-dimensional symplectic leaf, they have very, very special, how to say, stratification. And another stratification is also very interesting, but much more complicated. So this hypersurface, which gives you this level of polynomial, which is the centrum of this algebra, it's a hypersurface given by this equation. It means that you have a polynomial of degree 5, and the level 0 of this polynomial gives you some hypersurface. And this hypersurface may be considered like in projective space of degree 4. How much time I have? 10 minutes, okay, it's okay. So the second description is much more complicated, much more interesting. So if we have Q52, then the union of two-dimensional leaves is a cone, but not over the curve, but over the scroll, over the second symmetric degree of your elliptic curve, over two-dimensional surface in P4. And then to get description of four-dimensional leaves, we should introduce the notion of so-called three-secant variety for this scroll, for this symmetric square. I just want to say briefly, because I have no time, that all this geometry in P4, it is intimately related to so-called Horrocks-Mumford geometry, which was a subject of interest of algebraic topologists, algebraic geometers in mid-70s. And between mid-70s and mid-90s, they wrote a huge amount of papers about Horrocks-Mumford bundle. Horrocks-Mumford bundle, it is the unique non-decomposable holomorphic bundle on P4 with a group of symmetry degree of 15,000. So this is an absolutely fantastic object, and geometry of this object magically related to this geometry of symplectic leaves of Sklenin algebras. So the 3-second variety of the elliptic scroll X, it is just a union of all lines in this scroll which pass through the pairs xi xi1 and xi xi2, where xi you can fix and consider the curve corresponding in this product corresponding to this fixed xi. And then you can consider the set of y xi for all for fixed xi and all other xi1, and then you can consider the embedding of this curve. And this embedding, of course, you can consider in P2 projective embedding. But this P2 also depends on the fixed point xi. And so the 3-second variety X, it is a kind of cone over CP2 psi. This is a cone of this. This is a 3-second variety which I am interested in. Of course, it's generally it's a singular object, both secant and 3-secant. And in formal level, this variety is given also by quintic surface. And this quintic surface is a central polynomial for algebra Q52, similarly to Q51. To show the geometry of this, I need to remind the definition of birational transformations of projective space, which is called Cremona transformation. You have this polynomial function phi1, phi n, or phi 0, phi n. And so you have Cremona transformation if direct and inverse maps are rational. So this example of this transformation, just I will show you right now. Let's consider P4. Let's consider phi 0, phi 4. And then for given fixed point on CP1, we can consider the family of 5 quadrics. And then I need to explain you why this guy relates to our picture. Now, to embed normal elliptic curve in P4, you should take just the Klein description in terms of 5 quadrics, homogeneous quadrics, which are parameterized by point on S2, on CP1. And these Klein quadrics, in fact, they are not any, they are so-called syzygy of 5 times 5 skew-symmetric matrix of linear form in Klein classical book. If you find this book, it's very interesting. This book is about algebraic equation of degree 5, and Klein have a good geometric description of this embedding of elliptic quintic. The inverse transformation, which is by definition also rational, is given by cubic. This is also classical known object, which is in fact geometrically gives you this elliptic quintic scroll, Q lambda mu, it's equation of some surface. And this cubic surface gives you inverse transformation. So if you have direct phi and inverse phi minus 1, you have transformation of this secant in P4 with coordinates x to the scroll on P4 with coordinates z, and vice versa. And this theorem that if you take the choice of parameter lambda mu for Q51 and mu minus lambda for Q52, this quadricubic Cremona transformations, they are birational Poisson morphisms. This is, you can consider like small my result. And these Cremona transformations, they are exactly quasi-classical limits of quantum Adesky-Feygin embeddings Q51 to Q52 and vice versa. The Casimir, you also explicitly compute. How to compute the Casimir and to get this terrible, beautiful formula? You should take the secant variety, and you should take this parameter on P1, or denoted by A. I'm sorry, because, okay, no, A, it's okay, because second I will denote by K. They relate. So they are related by this condition lambda mu minus lambda. And then this polynomial, it is just Jacobian, determinant of Jacobian of the direct Cremona transformation. And Jacobian of inverse Cremona transformation of this cubic gives you centrum of Q51. And this Casimiran square. It is a degree 10 polynomial, but it is an exact square. And the parameter k in this polynomial relates to parameter a by this ak equal to -1. So geometrically, there is a nice picture. So you see here by dashed arrows, it is just a desingularization map. So you have P4 with coordinate x, and you have an elliptic curve here, and you have the secant variety here. This is in P4 with x. And you have P4 with coordinates z. You have this scroll here, and you have the 3-secant variety. And this scroll is a degenerate lossy for this 3-secant variety. Sigma y and sigma x, they are desingularizations of this secant and 3-secant variety. And these desingularizations, they can be considered like fiber bundles. This is a fiber bundles over the scroll, P1 fiber bundles. And this is a P2 fiber bundles over the very elliptic curve y. And the Cremona transformation, it is just combination of this desingularization by definition. And this map phi to this desingularized, to this desingularized, P4, which correspond desingularization of this scroll. And this P4, which correspond to desingularization along the embedded elliptic curve. So you have two Cremona transformation, sigma phi and sigma phi -1, direct and the inverse. And this is a full diagram which describes this geometry. Of course, I omit a lot of interesting details which I have no time to discuss. But it is interesting how to get this condition between lambda, between A and K. And this condition, you just write very stupidly, the Poisson condition for Heisenberg invariant quadratic algebra. So you start with given Poisson structure, and you want to find all other H invariant quadratic Poisson structures from this. And you think that you should you find 14 families. But only one from these 14 is non-degenerate. You have explicit solution of these conditions. And this explicit solution has one condition with this solution in terms of relation between A and K. And K is the 10th solution of this equation of degree K. And so you have exceptional solutions, and they correspond to degeneration of this Klein quadrics. Degenerate Klein quadrics defines the configurations of pentagons. So you have, in this paper, in this book of Klein, he called it Lectures on Icosahedron, because you can consider this P1 sphere. In this sphere, you inscribe icosahedron, and vertices of this icosahedron, they are a equal to 0, a equal to infinity, and 10 points of degeneration of lambda and mu, and correspondingly a and k from this. So you have 12 degenerate quadrics, which are not elliptic curves, they are rational degeneration. And they correspond to rational degeneration Skleinian algebras, which are deste without any geometry obtained by hand. And each pentagon corresponds to this degeneration of both algebras, Q52, Q51. You can find the correspondence between them. And only two are non-degenerate, Q51 and Q52. And this 12 degenerate. All number solutions, as I told you, 14. To finish, I want to say that there is a similar picture for n equal to 7, but it is much more complicated because in this case you have a triple of non-trivial different Skleinian-Odesky-Feygin algebras, 7.1, 7.2, 7.3, and their Poisson analogs. Then instead of P1, I didn't say you that this sphere, P1, it is nothing but show the modular curve in this picture. So the modular object here, it is a Klein quartic now. And of course, P4 is different from P6. On P4, there is this Horrocks-Mumford indecomposable bundle. In P6, you have nothing similar, so the geometry is much more complicated. But it is possible just to look few minimal interesting results. For example, if you have a cuspidal point on this Klein quadric, you have this similar to icosahedron degeneration of this Poisson Skleinian-Odesky-Feygin algebras. And also, you can consider, instead of 5 quadrics, you can consider 7 quadrics, and they will define you these Pfaffians of some linear CZG form. And you have a birational Poisson morphism between these 3 quadratic algebras. I know only, explicitly, I know only one of these 3. You have 1, 2, 3. But I know only one morphism explicitly by formulas. Thank you.